Hello, welcome to this video class. We're going to be talking about EMS research and evidence-based medicine. Our objectives today are going to be define evidence-based medicine, otherwise known as EBM, explain the benefits of evidence-based medicine. We're going to discuss the scientific method. We're going to discuss research methods and talk about why EMS research is important. So what is evidence-based medicine? It is the integration of best research evidence with clinical experience and patient values. Best research evidence, what is that? Clinical experience. Here we're going to be talking about your skills and your past experiences as individuals and collectively, your ability to think critically. And our patient values, we have unique preferences, concerns, and expectations from every patient, and understanding the risks and benefits of what we're doing and being able to express those and explain this stuff to our patients. So this is an example of how medicine was practiced before science. They had this idea. I'm not really sure exactly how this worked, but you have your four corners on the very back. You have your water, fire, earth, and air. Then you had on the next square in is hot, cold, opposite corners, wet, dry, opposite corners. And then further in, you have black bile, blood, opposite corners, yellow bile and phlegm on opposite corners. And then you have your circles, circle of life and how it relates to the seasons. But this was the idea. Again, this is Hippocrates back, 450 BC to fairly recently at 1858. So depression, they called melancholy blood. So this is kind of where medicine began and their idea of how everything worked together and integrated, and everything was done the same way for everybody without consideration of individuals and other things. So medicine has certainly grown a lot, and it's got quite the history of what we would consider today as quite barbaric. So why evidence-based medicine? So, well, prior to the 1970s, it was assumed that basic medical education, clinical updates, and interaction with other providers was adequate to guide good decision making. So basically, your initial education, the updates you're supposed to get, and then just conversation with your peers was good enough, and that should be sufficient for everything. Well, research in the 70s found huge variances on how providers would treat similar clinical conditions. And for any of you that were around back in the 70s or earlier, you may actually remember a lot of this. For younger providers, you won't remember this. But you could go, and depending on what doctor you went to, depending on where you were at, the treatment for asthma was different place to place. The treatment for myocardial infarction was different doctor to doctor. They all had their own view, their own idea, and their own way of practicing medicine. And you could literally go from one to another and get something totally different. Most patient care was based on tradition or experience rather than evidence and research. So one doctor would do it the way that he's always done it, and also incorporate in there, well, I've had these patients always did well when I did this, so I'm going to just continue to do that based on that experience. Again, it's that mentality. That's the way we've always done it. So why change? It's worked before. There's no reason it won't continue to work now. And so in essence, if you think about it, they were practicing at the level of graduation. So when they graduated medical school, when they were able to go practice on their own, they never really learned beyond that. So they were continued to practice at the same level throughout their careers. In 1985, the Institute of Medicine reported an estimate that only 15% of medical practices were actually based on solid medical evidence. Quite interesting. Again, it was, if you look at how they practiced, this is really a surprise, but at the same time, it's quite a surprise. So what it is a means to take the individual biases and common cognitive errors out of the equation. So evidence-based medicine helps to remove all of these things. It is also a means to keep up to date and evolves as the art and science of medicine evolves. So it's the continuation of the evolution of medicine. As new things are discovered, then they're put into practice and incorporated rather than just keeping and doing the same old thing the way that we always used to do it. As a means to apply rigorous review to what we previously just accepted as truth. So in the past, where a doctor said, then if a doctor said it, then it was so. Now it's with the way medicine is done and evidence-based, doctors practice based on evidence. And kind of the thing about it too is literally every single time you're treated, and a process is followed, that becomes a part of the evidence and the study, more or less. So, as part of that review process. So we're going to constantly reviewing and constantly seeing how we can improve, change, and make better everything. So what it is not cookbook medicine where, here's the problem, so here's the recipe to fix it, because that doesn't work. It tends to require more thinking to apply it correctly. So we have to be critical thinkers. It is not cost-cutting medicine. Sometimes the cost of care will increase, though the effectiveness will also. So you get more bang for your buck. So sometimes things decrease in cost, sometimes things increase in cost based on the evidence. We don't always, do things the way we used to. An example would be if you go to the hospital for a kidney stone, they do blood work, they do urinalysis, they can do an ultrasound. A lot of times this is done by CT now. In the past, they would do all these same things, but then they would do a series of multiple x-rays after you drank or were injected with dye, and watch the dye move through the kidneys and just kind of see where it backed up, more or less, which was a much more lengthy and a lot more radiation exposure. So we've gone to a more specific and solid practice. If you end up having a CT, it does cost more money, but you have less exposure overall because you can isolate a section that we're doing a scan of. We know exactly what we're looking at. A lot of times these things, like I said, are identified through just the history taking, the blood work, the urinalysis, and sometimes that ultrasound that's thrown in there because they can see lots of things with that. It is not a replacement for clinical expertise. So the doctors, the people that practice medicine, again, it's not cookbook medicine. So you have to apply critical thinking. You have to incorporate your education and everything about that to make expert opinion and expert decisions. And it is not a replacement for common sense. Goes without saying. It is not absolute rules and regulations that leave no room for deviation. Doctors always have room to base their medicine on the individual. That goes back again to that clinical expertise and not having cookbook medicine, and knowing your patients. So it's not absolute. So, when you go to the hospital for any condition, or to the doctor for any condition, again, they get a chance to vary their treatment regime and their protocols based on you as an individual and their expertise in areas and understanding of how everything interacts together. So now we're going to move on, and we're going to talk about the scientific method. You should be familiar with this from in school. Whether or not you remember it is something different. So this is the scientific method. It's just a simple chart, and we're going to go down this a little bit. So it strives to provide a reliable, predictable model. Provisional knowledge is required. It is reproducible, and it is unbiased. So the first thing you're going to do is you got to ask a question, and then you're going to do background research. You're going to, based on that question and that research, you're going to construct a hypothesis, and then we're going to test that hypothesis with experiments, and then we're going to look at those experiments and analyze the results. We're going to draw our conclusions. We're going to determine, was our hypothesis true or was our hypothesis false? If our hypothesis is false, we're going to go back up and we're going to rethink, and we're going to revise our hypothesis, and then go down and test that hypothesis again, analyze the results. And if our hypothesis is true, we're going to report our results. That is the scientific method. So here is an example, the scientific method. So an observation is, well, during a discussion, you and your coworkers bring up the idea that there are more psychiatric emergencies when the moon is full. So that's going to be your question. So the scientific methods is, we're going to have a prediction, and my prediction is that there will be more EMS calls for psychiatric emergencies when the moon is full as compared to other times of the month. So we're going to have a study method for our testing. So we're going to set up an experiment protocol to test our hypothesis. And so what we're going to need is the study method, the study period, the study parameters, a study group, and a control group. So you have all these things in order to do this, to test the hypothesis. So my study method is going to be a chart review, which is also known as a retrospective review. We're going to establish a study period, and so we're going to review charts for the for the period of 1 year. Our parameters is, we will review all charts over this period. We must define what constitutes a psychiatric emergency, and then we're going to gather information over the course of the year that includes the date of all psychiatric emergency patients. So our study group, we're going to have all patients that occur in your quote full moon period. So we have to define that, and it's going to be defined as 2 days before and 2 days after the full moon. So we're looking at a 5-day period. Our control group is going to be all other patients' contacts outside of the full moon period. So what do we find when we do our experiment? Our results. We're going to see here that we have full moon period that totals 65 days, where our other periods outside of the full moon is going to be 300 days, for our total of 365 days for 1 year. In our full moon period, we had 10 patients. On our period outside of our full moon, which is our control group, we had 74 patients for a total of 84 patients. So our total patients altogether was 2,105 patients, but our total patients during the full moon period was 2,105 patients. Our total patients outside of the full moon period is 9,300 patients, which totals 11,315 patients altogether. So now we're going to crunch some numbers and do some math. And so here's what we find. We find that during full moon period, we have 0.5% of patients who were psychiatric patients. During our other periods, we had 0.8% of patients that were psychiatric patients. During the entire study, we had 0.7% of patients that were psychiatric patients. So now, this is what our results are. Now we're going to go a little further and analyze and look into these results. And so what we find is that our incidence of psychiatric patients during the full moon period was 0.15 patients per day. The incidence of psychiatric patients during other moon phases was 0.25 patients per day. And the incidence of psychiatric patients overall, with the combined of those, is 0.23 patients per day. So what does this mean? Our psychiatric patients are less common during the full moon. So our hypothesis has been disproven, but that's okay because this is science. The results are what counts, not our assumptions going into the experiment. So now that we have looked at this data and we have proven through this one study that the theory that psychiatric calls are going to increase during a full moon period is not actually true based on the data that we have in front of us. So now what are we going to do? Well, we're going to revise our hypothesis. In order to make our hypothesis true, we're going to redefine that and say that psychiatric emergencies are no more frequent during the full moon lunar phase than during other lunar phases. Based on research, this hypothesis is now accurate. That is, until it is disproven. So this, again, based on one year's data from one particular service, is showing that this hypothesis is not true. But this can be repeated by other people, by other places. It can include more data, more whatever, and see if this hypothesis now holds true or if there is conflicting data. So now what do? We tell other people about it so they can benefit. We publish our findings, write a paper detailing how we did our research and what our findings were. We can repeat the study to ourselves. Other people can repeat the study because we've told them how we did the study. And we'll see if this holds true in other systems. This could be a small part of a much larger study. Are there any weaknesses in your study that could be corrected? And if there are, we can do that so that they can be avoided in new studies. All right, so now we're going to look at our quality of our evidence. And so we have this hierarchy here of this pyramid, and we're going to talk a little more about that. We have all the way at the bottom, background information, expert opinion, and non-evidence-based medicine guidelines, all the way to the top, which is going to be our meta-analyses. So this is kind of the hierarchy of how all this stuff works. So at the bottom, we have our, this is animal laboratory studies, no humans are involved. You have kind of the expert opinions and editorials and narratives. It's, just more of an informal kind of thing, kind of putting everything together. And then we're going to start building our hypothesis. We're going to have everything together, and we're going to start our controlled studies. There are different types of controlled studies and things we're going to look at in the primary area. We have the observational studies at first, the case control studies and our cohort studies. And then next we move into our randomized controlled trials, and retrospective test treatments. And then from there, we're going to go to the top of the pyramid, which is the elite of all the evidence-based medicine. And we're going to look at our meta-analysis system reviews. We're going to write clinical practice guidelines, which then are going to go into review and all these type things. So our RCT, random controlled type, are the gold standard for primary studies. Our meta-analysis and system reviews are above that. And all of this leads to evidence-based guidelines. So we, as medicine, as processes, as devices, as things go through this study or this process, then once we reach the top of the pyramid, then that is the gold standard, and that is where we want to then start to base practice on the data results. So we're going to talk here a little about a randomized controlled study. So randomized controlled trials is, again, the gold standard. So we have a group of patients who are randomized into an experimental group and a control group. These groups are followed up for variables and outcomes of interest. So as they go through this study, we're just collecting data. We're looking at that data. Randomized controlled trials, they're most closely approximate the scientific method, and they are the most valid of the studies. So really the gold standard here is the double-blind study. You may or may not have heard of what that is, but what it is a study in which neither the patient nor the physician knows whether the patient is receiving treatment of interest or controlled treatment. So the patient has agreed to be a part of the study. The provider, physician, whomever, is also obviously a part of the study, but the treatment that patient receives, neither one of them knows if it's the experimental treatment or the standard treatment. That is only known back to the research team, so that it takes out all bias. So they just collect the data, they do the treatments, the protocols, or whatever it is, and the data goes back to the team that is working on that, and they are the only ones that know if a person received the experimental or the traditional treatments. So we have cohort studies. A cohort study here is where you have patients who presently have certain conditions and or receive a particular treatment. They're followed over time and compared with another group who are not affected by the same condition under investigations. So an example here is you have your group of interest would be smokers. Your comparison group are non-smokers. So what do? We follow smokers over time, and we follow non-smokers over time, and we collect data, all kinds of different information on them, and then we're going to compare the outcomes. And this is basically how they have determined that smoking is bad for you. Smoking causes cancer. Smoking causes COPD. And it increases the instances of all these things, and that's how they are able to come up with percentages and numbers based on this type of a study. The next thing we're looking at here are case control studies in which patients who already have a certain condition are compared with patients who do not. So you have somebody that has conditions versus somebody that does not have conditions, and we're going to compare the two and draw conclusions. So on the right side of this chart, we have a group of cancer patients and a group of non-cancer patients. So what we're going to do is we're going to take their histories, and we're going to compare what we find and draw conclusions. So based on this, we find things such as persons that are exposed to cigarette smoke have a high instance of cancer. Persons that are exposed to certain chemicals are going to have high instances of certain types of cancers. People that are in certain groups, such as firefighters, have higher instances of certain types of cancers. And so that is what a case control study is. So a case series is a report on series of patients with an outcome of interest. There is no control group involved in this particular study. So this is the one time, I had a bunch of patients with the ABC condition, and we did XYZ treatment, and here is what happened as a result. Honestly, this reminds me a lot of the coronavirus and the way various providers were treating coronavirus and how we had a lot of conflicting information given to us. So everybody had coronavirus, and one provider would prescribe this regimen of treatment, and the results were XYZ. And another provider would basically do the same types of things, and they would publish and say, well, I did this and I had a good outcome, or I had a poor outcome. And that's what this type of a study or a report is. A case report is a narrative report of a single interesting case. So it is what it is. We have reviews. A meta-analysis is a systemic review of multiple studies that have already been done, rather than conducting a new study to draw conclusions based on the whole of the studies. So here, somebody is taking a bunch of different studies that have already been done on a particular disease, medicine, process, or whatever, and they basically go back through the studies, they re-review everything, they compile everything into one data bank, one group, and then they can further develop conclusions and base things off of a much larger group than maybe a lot of smaller group individual studies. An example would be the psychiatric cause during full moons. We saw one study disprove that theory, but you might have multiple studies over multiple states, multiple jurisdictions, and you may have varying outcomes. And so a meta-analysis of that data would be to take all of that data to compile it into one, and instead of having a patient sample of 11,000, now we have a patient sample of 300 million, and you're going to have much better statistical data as a result and be able to produce much more statistically sound results as a result of combining all this stuff. So we take study 1, 2, 3, and 4, and we're going to combine all these results with this meta-analysis, and we're going to look and see what the totality comes out as. So the meta-analysis of random controlled trials represents the highest level of scientific evidence. So again, we're taking multiple high-level studies and combining them into one. So this is based on a theory that multiple random controlled trials will show more truth than a single random controlled trial will, such as I've already explained. This allows for more objective appraisal of the evidence and reproduces the possibility of false negatives or false positive results. So they're just digging deeper and looking more into all this stuff. So is science perfect? Absolutely not. It is not perfect, but it is the scientific method itself acknowledges that it is not perfect, and the continuation and reproduction of the studies over and over is what helps to perfect as best as possible the outcomes. And that is how our medicine now is being driven. It's been that way a long time for in-hospital and long-term type practice, but has not so much made it out into the world of EMS as quickly. So what has changed? Well, does anybody even know what this is? Certainly the older people, the older medics will know what this is, and this is masked trousers, anti-shock trousers, you may have heard. And we do no longer see those in the state of Georgia, and I'm not so sure about other states as well, honestly, because we have proven that they do not do what they were thought to have done. There are some good uses for some of these, and some people have had good luck with them in the past, but the vast majority, it just does not work the way that people thought it did. How about positioning? Fowler's, semi-Fowler's, Trendelenburg, reverse Trendelenburg. So we do all these, studies now, and we know that different positions are good for different treatments of different issues. Some positions are bad for certain issues, so we don't go there. How about flight? How flying people from scenes, flying people from hospital to hospital. Lots of studies in the past have gone on with this. Lots of studies continue with this, and the usage of air evacuation. So that's something that is continuing to change. This is, I wish I had the video, but I don't. But this is the back of an ambulance, and you can actually watch them. They're really interesting to watch. Crash tests for patient positioning, for patient restraint, for passenger positioning, passenger restraint. You see the net up there. Nets and barriers there didn't used to exist, but based on injury patterns and based on testing, that's why nets are now at the front of the bench seat. The positions of the seats, the way the seats are made, we used to only have lap belts on our bench seats. Now we actually have individual seats with lap and shoulder harnesses. It's like a race car. Patient restraints, stretcher designs. Why do we have our self-loading, or not self-loading, but assisted loading, I guess you might say, stretcher systems? Why are they secured the way they are? Why does our stretchers now have shoulder straps on them? It's all because of evidence. It's all because of the evidence-based studies that have been done to help improve the safety and security of ourselves and our patients in the back of ambulances. I would advise you to look up some crash test videos and watch some of them. Quite impressive and somewhat scary at the same time. So what other things might change? All kinds of things can change. I'm not sure that if any of you remember this, but in 2018, this was published. Epinephrine for cardiac arrest, better survival, more brain damage. So we can look over here on the right and look at this data a little bit. So we have an area here that says no disability, no symptoms at all. We have no significant disability, some symptoms, but able to carry out usual duties and activities. We have slight disability, so this would be unable to carry out all previous activities, but able to look after your own affairs without assistance. You have moderate disability, so that will require some help, but you're able to walk without assistance. You have moderately severe disability, so unable to walk without assistance and unable to attend to your own bodily needs without assistance. And then you have severe disability, so bedridden, incontinent, and require constant nursing care. So of these patients, you had 126 that were given epinephrine and survived in cardiac arrest, and you had 90 patients who were not given epinephrine and survived cardiac arrest. So of all this, we look and we see that the patients that had no disability, 126 were given epinephrine, 9.5% came out with no disability. The ones that did not have epinephrine and survived, 16.7% had no disability. And you can read on down this, and it's quite interesting. And according to this study, we see that when we get somebody back from cardiac arrest and we have used epinephrine, they may survive, but they have a very high chance of having some sort of brain damage, all the way up to severe. You have moderate disability at 27.8% and severe disability at 21.4%. That is pretty high. This is one study. Other studies need to look at that as well. And you can see at the bottom, this was a double-blind trial, more than 8,000 patients in Great Britain. So this is how this works. This is what we come to find when we follow evidence-based medicine. We do these trials. So when you hear about, should we leave epinephrine in ACLS? Should we take epinephrine out? We've changed from lidocaine to amiodarone. Now we're going back to lidocaine, based on studies. And it's not just about survivability, but it's about quality of life. At one point in time, we had what was called and known as high-dose epinephrine in cardiac arrest. We got a lot of people back, and we got a lot of people that ended up in nursing homes, or most of them actually just eventually died within a day or two, if not sooner. So we had, basically, it wasn't doing any good for our patients. We were incurring lots of costs for critical care, for ICU, for long-term care facilities, for people in vegetative states, because we gave them high-dose epinephrine. And so that has since been removed. It was only in there for a few years before it was removed. So we have to look at the entire package when we see changes and when we see things that we may disagree with. We need to learn to read this research. We need to learn to look at it. So how EMS data saves lives. So we look at all this stuff, the data that you're asked to collect, the data that that you don't want to collect. Fill in the box here, fill out the dots here, and all these things. The one thing that is definitely true is if you don't have good data in, you're not going to have good data out and good results, good practice stuff out. So we need to make sure that we are collecting proper data. So as we look through here, what could EMS providers do better? So we can collect data. We can start to answer some of these questions. We can look at this EMS systems and how can EMS systems improve your response. When we look at response times in rural versus urban, and all kinds of different things, we can start to find answers. What does the patient need now? So when we have patient encounters for various types of things, we can start looking at trends, and we can look and see how patient groups are reacting or maybe need to be treated differently for whatever reason. How can EMS reduce deaths and injuries on the highways? So there's lots of different things that are ongoing studies in EMS that you may know about, you may hear about, you may see in the future. So here are some things that we find. We have the age of people in motor vehicle crashes treated and transported by EMS in the year 2012. So 39% of people that were in automobile accidents and were treated and transported by EMS is 39%, which is the majority of this particular information. So that could lead to all kinds of questions and studies to look at, why is it this age group? Is this the largest age group that's out driving? I don't think so. Is this the largest age group where people think they're invulnerable and people think that they can handle it? More than likely it is. So we can start to ask questions and have follow-up data. We can have follow-up studies and drill deeper into some of these things. Top right, we're going to look here at most states that have adopted uniform EMS data collection. And you can see that the vast majority of the states at the time this was published have a uniform way of collecting that data. And then there are most everybody else is getting ready to be on board if they're not already. So now we can look down here at the national EMS system by the numbers and look at the different numbers and types of response times and everything. On the far right, on the bottom, we'll look at bicycle crash data. Quite interesting statistics. So this is how the statistical information that we put in those reports are being used. And there is the National Incident Report system. Georgia also has their own system that we dump our information into the national system. And so it's important to get the numbers accurate, the data accurate, so that we can have good data to work with. So this is actually something that was published. There's a new publication out. I will attach as a separate attachment into this training, and it is more current data. But this is quite interesting, this ESO EMS index. And this particular one looked at 5.02 million patient encounters January 1st through December 31st of 2017 across a number of events at the macro level. And the index revealed the following 5 metrics. So it was quite interesting that 50% of the situation and 50% of situations, a complete stroke assessment was documented for a primary impression of stroke. So what this is saying is that for all the patients that were labeled as a stroke patient, only 50% of them had a stroke assessment documented. This shows that we have a significant room for improvement. We look over to the right, we have EMS providers recognize the value of end-tidal CO2 monitoring after advanced airway placement. 94.5% of cases, end-tidal CO2 monitoring was initiated after advanced airway insertion. So this is how we can prove to say that we're monitoring these things, that when we put in an ET2, we have a way to definitively monitor that and to look at that. Below that, we have 12-lead performance and chest pain still needs attention. Only 75.9% of non-traumatic adult chest pain encountered received a 12-lead EKG. That makes no sense to me. If you have a complaint of chest pain, for the most part, you really should be getting a 12-lead. There's probably exceptions to the rule, but for a non-traumatic chest pain, we need to be getting 12 leads, and only 75.9% did that in this particular data set. So there's room for improvement. Next, down over on the left, we have overdose encounter outpaced cases where stroke is a primary impression. So there were nearly 12% more overdose cases reported in 2017 than strokes, aligning with much of what paramedics are reporting the last few years. So now we're starting to look at some statistic stuff, so showing the prevalence of overdose when we compare it to strokes. And we can see that it is going up. Next over, we have aspirin administration is hit or miss. Just more than half, 55.3% of reported cases of non-traumatic chest pain patients over the age of 35 received aspirin administration for chest pain. There's plenty of room for improvement. There's virtually no downside to give aspirin for somebody with chest pain, unless they have an allergy or they have a significant bleeding risk or something like that. So 55.3% is a fairly low number. And then our last one is more men than women overdosed. Men accounted for 28% more overdoses than women. And that's just, plain statistical data. So 20 men overdose at a higher rate than women. So this is the kind of data we can get. This is the kind of things that start making you ask questions. And when you look at data trends over time, you can start finding a lot of answers, and it's going to support all kinds of things. It can be used to support budgetary processes, requests for different things, protocols, procedures, um, carrying new medications, getting rid of old equipment that's not used, that's not necessary, all kinds of things. So evidence-based medicine is here to stay, and it is something that is important, and we need to learn to use for our advantage. We need to learn to look at the studies and ask the questions. And one of the most important things is you never make a decision based on one study alone. You always make decisions based on multiple studies. And that's why the meta-analysis are so important, because that's exactly what they do. They look at a lot of data, multiple studies, and not just one, um, without going into how to read and all the things that go behind that. You have to have supportable documentation for everything, including studies and reasons for making decisions and changes. If anyone has any questions, contact the training department. Thank you.